archival or recreated footage of a heavily loaded transport plane struggling on a short runway, engine screaming, tires smoking. Cut to black and white historical crash footage or simulation of wing stall at low speed / high weight. Overlay text, lift versus weight, the eternal trade-off. Imagine you're an engineer in the 1980s. The Pentagon wants a single aircraft that can haul an M1 Abrams tank or over 100 paratroopers across an ocean, and then land on a dirt strip barely longer than a football field. On paper, it shouldn't work. The basic equation of flight is brutally simple. Lift must equal weight. But for heavy cargo at low speeds, you need enormous wing area or extreme angles of attack. Push the angle too far, and the boundary layer separates. Airflow detaches from the wing, you stall, and you crash. For decades, strategic airlifters like the C-5 could carry massive loads but needed long, pristine runways. Tactical aircraft like the C-130 could use short fields but couldn't cross oceans with heavy payloads. The physics barrier seemed insurmountable. You can't optimize for both range and short field performance without breaking the laws of aerodynamics, or so everyone thought. Map animation showing Fort Bragg, North Carolina to Middle East bases, e.g. Al Udeid, Qatar, or Jordan. Timeline of recent 2026 deployments. Icons of C-17s flying overnight, 82nd Airborne troops boarding. Graphs of payload versus distance for different aircraft. In early 2026, amid escalating tensions, the U.S. moved thousands of elite soldiers from the 82nd Airborne Division, America's premier rapid response paratroopers, to the Middle East. Reports indicate several thousand troops, supported by a massive surge of over 100 C-17 flights earlier in the year, delivering not just personnel but vehicles, equipment, and supplies directly into theater. This isn't just logistics, it's power projection. In a world of contested airspace and austere forward bases, the ability to deliver combat-ready forces overnight changes the calculus of deterrence and response. The economic and military driver is clear. Speed beats mass when geography and politics limit naval or ground routes. But to do it at night, with heavy loads, over vast distances, you need an aircraft that defies the usual compromises. Animated force diagrams, lift, weight, thrust, drag. Bernoulli's principal animation versus Coanda effect. CFD simulation of airflow over a conventional wing stalling at high angle of attack. Graph, lift coefficient CL versus angle of attack, showing stall point. Cut to C-17 wing with engines highlighted. Why is this so hard? Start with first principles. Lift is generated primarily by accelerating air downward over the wing. Newton's third law in fluid form. The lift equation is L equals 1/2 rho V superscript 2 SCL, where rho is air density, V is velocity, S is wing area, and CL is the lift coefficient. At takeoff and landing velocity, V is low, density, rho, is whatever the airfield gives you. So you need massive south or high close high CL, usually means high angle of attack, which invites stall as the adverse pressure gradient causes a boundary layer to separate. Traditional high lift devices, slats and flaps, help, but they add drag and complexity. For a true strategic / tactical hybrid, you need something more. Enter the core constraint. To land heavy on short runways, you need steep approaches and high lift at low speed without stalling or floating forever down the runway. But jet engines produce thrust in a narrow exhaust stream, most of it wasted if not used cleverly. Exploded or cutaway view of C-17 wing and engines. Slow motion animation of externally blown flaps. Engine exhaust visualized as colored flow being directed over / through flaps. CFD simulation showing increased lift from blown flaps. Fly-by-wire control system diagram with redundant computers. Night landing footage with thrust reversers deploying. Engineers solved it with a deceptively simple but physics-savvy trick. Externally blown flaps. The C-17 mounts its 4 Pratt & Whitney F-117 PW 100 turbofans, each producing 40,440 pounds of thrust, derived from the commercial PW 2000 series, forward and inboard. The exhaust is deliberately directed over and through large, triple-slotted flaps. This blows high-energy air across the flap surface, energizing the boundary layer and dramatically increasing the effective CL, often by 50 to 100% at low speeds. It's not magic. It's the Coanda effect and momentum transfer at work. The engine exhaust sticks to and follows the curved flap, turning the flow downward more aggressively. Result: you can fly at steeper angles of attack without full stall, achieve shorter takeoff and landing rolls, and still carry up to 170,900 pounds of payload. Add a supercritical wing for efficient high-speed cruise, around Mach 0.74 to 0.79, leading-edge slats, and a fully digital fly-by-wire system with triple redundancy. The aircraft can operate from runways as short as 3,500 feet by 90 feet wide. Even perform a three-point star turn or backup under its own power, using those clever upward/forward-directed thrust reversers that also minimize foreign object damage on dusty Middle Eastern strips. For the recent midnight operations, this means C-17s could depart U.S. bases, refuel in flight if needed, and deliver 82nd Airborne troops and equipment directly into forward areas under cover darkness, with terrain following radar and advanced avionics, reducing crew workload. Graph comparing fuel burn. C-17 versus older airlifters. Animation of high fuel consumption during low speed/high lift phases. Cost overlay. Acquisition and operating expenses. Heat and maintenance visuals on engines. Real engineering is compromise, not perfection. The blown flap system is brilliant for lift, but comes at cost. Higher drag and significantly increased fuel burn during takeoff and approach phases. The C-17 is thirsty, one of the Air Force's bigger consumers of jet fuel. To achieve its unrefueled range of roughly 2,400 to 2,800 nautical miles with a heavy payload, depending on variant, it relies on efficient crews, but the short field capability trades some overall efficiency. Weight is another factor. The massive structure needed to handle 585,000 pounds maximum takeoff weight, plus the reinforced cargo floor for outsized loads like armor vehicles, adds structural mass. Materials science helps, composites and high-strength alloys, but nothing violates a rocket equation equivalent for aviation. Every extra pound of structure reduces payload or range. Maintenance is complex. The fly-by-wire and high-lift systems demand rigorous upkeep, and while it's more reliable than predecessors, operating in austere desert environments stresses the engines and reversers. Popular misconception: the C-17 is a do-everything miracle with no downsides. In reality, it's a carefully balanced machine optimized for the U.S. military's unique global reach requirements, not the cheapest or most fuel-efficient option for every mission. Summary infographic, payload range, runway length comparison table, C-17 versus C-5 versus C-130. Cost estimates, rough acquisition, $200-300M per aircraft historically, high operating costs. Future concepts, blended wing or more efficient engines. So, is the C-17 viable for the future? Absolutely. It has been the backbone of U.S. air mobility for decades precisely because it solves the strategic tactical gap better than anything else. It's not a prototype. It's proven in conflicts and humanitarian crises worldwide. Economically, each aircraft is expensive to buy and operate. Fuel, crew training, and sustainment add up fast when you're surging dozens or hundreds of sorties, as seen in recent Middle East buildups. It's cheap enough to maintain America's edge in rapid deployment, but not so cheap that it democratizes heavy airlift globally. Future upgrades or successors will likely focus on better fuel efficiency and even smarter high-lift systems to push the physics envelope further. Montage. C-17 taking off at night. Troops unloading in desert. Smooth transition to animated atoms/molecules of airflow, then wide chauffeur from space with aircraft contrails. Ultimately, the C-17 isn't about defying physics. It's about intelligently working with the laws of aerodynamics, fluid mechanics, and materials. Humans didn't break the rules of lift and drag. We found the cleverest way to stack the deck within them. In an uncertain world, that kind of first principles engineering doesn't just move troops at midnight. It moves history. Subscribe, like, comment. What other military engineering topic next? Sources and further reading.